Diagonalization failed because one eigenvector was not enough. Today we name the leftover behavior instead of pretending it politely vanished. The two names are nilpotent operators and Jordan blocks. They sound dramatic because apparently matrices needed Gothic architecture. An operator n is nilpotent if some power of n is the zero operator. In plain language, repeatedly applying n eventually kills every vector. Not immediately, necessarily. It likes suspense. Because of course it does. The simplest non-zero nilpotent matrix sends E2 to E1, and sends E1 to 0. Square it, and everything is gone. A 3x3 version shifts one step down a chain. After 3 hits, even the matrix runs out of excuses. But not every matrix with 0 somewhere is nilpotent. This projection survives every power. 0 entries are not magic dust. Sadly. A nilpotent operator naturally creates chains. A vector moves down the chain, then eventually lands at 0. With the basis ordered from the bottom of the chain upward, the matrix has ones above the diagonal and zeros everywhere else. A tiny conveyor belt to oblivion. A Jordan block has one eigenvalue lambda on the diagonal, ones just above the diagonal, and zeros elsewhere. So a Jordan block is diagonal behavior plus nilpotent chain behavior. It is what diagonalization becomes after reality starts charging rent. A 1x1 Jordan block is just a diagonal entry. That is the boring case, and therefore the most popular one in beginner examples. Blocks of size bigger than 1 are where generalized eigenvectors appear. They measure exactly how diagonalization failed, instead of just pointing at the wreckage. Subtract lambda I from a Jordan block, and what remains is nilpotent. It moves each chain vector one step toward the eigenvector. This is why Jordan chains are not decorative notation. They are the coordinate system that makes the failure of diagonalization readable. Here is the theorem we are heading toward. Over the complex numbers, every linear operator on a finite-dimensional vector space has a basis where its matrix is block diagonal with Jordan blocks. So diagonalization is not the whole story. Jordan form says, if you cannot diagonalize, then at least fail in standardized blocks. Bureaucracy, but useful. Nilpotent operators describe chain movement toward 0. Jordan blocks combine eigenvalue scaling with that nilpotent movement. Next, we start proving that over complex vector spaces, every operator can be organized into these blocks. Naturally, the universe waited until now to become tidy.